So we're going to look still at finding the area between two curves, but now we're going to look at using horizontal rectangles. So I didn't really specify before when I gave you that formula of top curve minus bottom curve. Really what we were doing is looking at rectangles. And the reason I know we're looking at rectangles is because when we first introduced integration, we talked about how we were finding area by looking at rectangles as a way to approximate. And then, so we started by looking at maybe 4 or 5 rectangles and then said, well, what if we expanded and we created more and more rectangles to the point where our number of rectangles, or our width between rectangles was, or the width of our rectangles was approaching infinity. And we talked about how that was going to be the definition of an integral. So that's how I know I've been using rectangles, because I've been integrating. So we're going to look at this example twice, once with how we've been doing it, and then I'm going to show you another way to do it with horizontal rectangles and show you how that differs. So the first time we look at it, we're going to look at finding the area between top curve and bottom curve. And we're going to go ahead on both of these, and we're going to let our limits be x equals 0 and x equals 4. So my bottom curve I'm going to let be g of x equals 0, so I'm going to go ahead and put those instructions in there. So I'm going to go ahead and find area between f of x, which is listed above, and g of x equals 0, and my limits are going to be x equals 0 and x equals 4. So my g of x equals 0, remember, is this line down here. So I'm finding the area between this line, and I don't have a very nice smooth curve because I tried to draw it with a mouse, but essentially this curve here. I don't know if that made it better or worse. And then x equals 0, which is here, and then let's say x equals 4 is here. So I'm trying to find this area here, so I can clearly see that x squared is my top curve. And what I'm really doing is I'm going ahead and I'm looking at all these little rectangles that make up this function. And when I do, remember we talked before about how we take the area of a rectangle, which is base times height, and I can call the base whatever I want because I'm not specifying the width of this rectangle. So maybe I call it dx, and maybe I call my height. I get my height by plugging back into my function here, so I call that f of x. And if I were to draw a whole bunch of these rectangles and then take the limit, then I would get that integral. And the integral I would get would be the integral from 0 to 4 of my top curve, which is x squared, minus my bottom curve, which is 0, so I can neglect that, dx. From here I can put that in my calculator, and I get 64 thirds. Again, that represents the area between those two curves. Well, what if I looked at that same function, but instead of being between f of x equals x squared and g of x equals 0, what if instead I said I want to be between this curve here and g of y equals 0? Well, this implies that my x value is 0, so now I'm looking at this curve, which is in fact a straight line, and this same curve that I already looked at here. And let's say I still say x equals 0 and x equals 4. Well, actually I'll get back to that x equals 0 and x equals 4 in a moment. Notice now it's very hard for me to draw in those rectangles unless I turn them sideways and put in horizontal rectangles. Well, everything works the same way, but now instead of everything being in terms of x, I'm going to put everything in terms of y. So I'm still finding my area. And so the first thing I'm going to do is I'm going to, because now I'm using horizontal rectangles, is I'm going to go ahead and I want both of my equations to be in terms of f of y. So I'm solve each equation for x. Which, notice that this second one is already g of y would be like saying x. I'm already in terms of x. This is the same line as x equals 0. F of x equals x squared. If I solve that, and notice I don't need the plus or minus since I am just in that first quadrant, I'm going to go ahead and say y equals the square root of x. And then I'm going to go ahead and I'm going to find my limits. And my limits need to be in terms of y. So if I was already told that x is between 0 and 4, so I mentioned I was going to use this for both, I'm going to go ahead and plug 0 into this equation to figure out what the y value is. So y equals 0 squared, which equals 0, and y equals 4 squared, which equals 16. Well, once I have all that, I'm going to go ahead and I'm going to integrate, and when I integrate, when I'm using horizontal rectangles instead, I'm going to do right curve minus left curve. Similar to with vertical rectangles when I do top curve minus bottom curve. So now it's going to be right minus left. And you're going to see this become a lot more solidified and a lot more important when we start talking about solids of revolution and we start talking about them going around an x versus axis versus a y axis. So if you're a little unclear of why do we have two separate rectangles, that's okay. Like I said, this will become a lot more solid as we kind of move forward in here. So now I'm going to go ahead and integrate. So I'm going to go ahead and write my integral, and my y limits were from 0 to 16. And my right curved was my square root of x. And my left curve was just 0, so I don't need to write it. And it wasn't square root of x, that should have been square root of y if I solved that correctly, because f of x means y. Square root of y equals x. That sounds better. Now I've actually solved for x like my directions told me to. And then I have dy. So again, as we've looked at before, I do have same variable there. Then I just put that into my calculator, and I get 128 over 3. Let's go ahead and look at example 2. So on example 2, it'll become a little bit more clear again as to why horizontal rectangles can become important. So on number 2, I'm going to go ahead and make this line in there for the fraction. On example 2, I have the exact same thing written twice. So let's say I go ahead and I look at this and I think, oh, if I have to find the area between these two curves, all I'm going to go ahead and do is do top curve minus bottom curve. Well, when I look, again, if I make this a little bit smoother, I see that, yeah, this is my top curve. I can see that there by drawing in my rectangles. It makes it very clear which is my top and which is my bottom. Top curve and bottom curve, top curve and bottom curve. But notice that right about here, I start running it into an issue because my top and bottom curves change. So I can see fairly clearly that up until about this point here, my top curve is this one here, and x minus 1 is my bottom curve. But here, notice that this is both my top curve and my bottom curve. So I run into this issue when I'm drawing in these vertical rectangles that my top and bottom curve change. And we have seen that before, and we've just went ahead and made more than one integral. But I want to point out that if instead of doing more than one integral, you could do horizontal rectangles. So if I look at this same example, so I look at this same curve, notice that this is always my left curve. And this is always to the right of that curve. So it seems like I could just do one integral if I looked at this. Looked at it using horizontal rectangles. So the first thing I'm going to do is I want to solve both equations for x. So I see the first equation is already solved for x. The other one I'm going to go ahead and add 1, and I'm going to get y equals x plus 1. Then I need to find my limits. Well, I know that to find my limits, I can find the intersection point between my two curves. So if I set these equal to each other, I can go ahead, and I did it again. I'm, for whatever reason, really struggling to solve for x. So if I added 1, I would get y plus 1 equals x. I've just rewritten the original problem. Now I can go ahead and say, since both of these are equal to x, I can set them equal to each other. Y squared over 2 minus 3 equals y plus 1. I can get rid of that fraction by multiplying everything by 2. And then I can see this is quadratic, so I'm going to get everything over to one side and I'm going to factor. So I get y minus 4 times y plus 2 equals 0. So I can see that my two limits are going to be y equals 4 and y equals -2. So then from here I can go ahead and integrate from -2 up to 4, and I will do right curve minus left curve, and I've pulled it up just a little too far. I can't see my curve. There we go. See if I can't get my integral and my curve in the same screen. So my right curve was y plus 1 minus, to show I'm subtracting that entire curve, I will put it in parentheses. And now from here I can just go ahead and put this in my calculator. Putting this in my calculator, it integrates it for me, and I do get a value of 18 as my final answer. So as I said, it may be slightly unclear as to when do I use, or why would I want to learn this other way of changing everything to be in terms of y's. But the big thing is then I can kind of avoid some of those multiple integrals. I can just create one integral. And as I stated before, as we move into rotating these curves around an axis, it will make a lot more sense when we're rotating around a y-axis versus an x-axis, why we have to choose specific rectangles. But for now, a good indicator of check to see if you want to use horizontal rectangles is if you switch top curves at some point throughout your diagram. Otherwise, bring questions bring the questions you have with you to class, and we'll go over them before you get started on the practice for this.